Hello, good morning, everyone. Welcome to the NICKEFFECT and NOUVEAU webinar on water electrolyzers for a sustainable future. Today in this session, we present NICKEFFECT and its work on PEM water electrolysers and the NOUVEAU project that will dive into the SOEC technology. This session is ideal for researchers, industry professionals, and students interested in cutting-edge development in electrolyzer technologies. If you are interested in exploring innovative solutions in energy systems and understanding how these technologies are shaping the future, just keep watching. At the end of the session, we will have time and a space dedicated to a Q&A, so feel free to drop your questions in the chat in the meantime, and we will make sure at the end of the session, everything will be answered. So we will begin with our speaker from the NICKEFFECT project, Frederic. He's our project partner from CEA. His presentation will be around materials for electrodes of PEMWE challenges and perspectives.
So thanks for this nice introduction. So my name is Frederic Fuda Onana from CED10 in Grenoble. And my talk will be today on PEM water electrolysis and to introduce how NICKEFFECT project want to challenge the main issue, some of issues in PEM water electrolysis. So, yeah. On that slide, I show the outlines that will be discussed during this presentation. So I will start with why we need the green hydrogen and to reach the cornerstone about net zero emission by 2050, how PEM water electrolysis could reach this target with some strengths and weaknesses. And then I will also have a discussion about what kind of alternative material could be used as the cathode side of PEM water electrolysis, and how NICKEFFECT want to provide some alternative to platinum. And I will end my speech with challenges and the future outlook. So, yeah. Yes. So my first slide here is to express why we need the hydrogen. So basically, people are used to think that hydrogen is mainly used for mobility, for low-duty vehicles, as example, but actually the main use of hydrogen is for chemistry, ammonia production or petroleum refining. There is also stainless steel used where we need the hydrogen. So actually, hydrogen is not really used only for mobility. So yeah, by far, the chemical and refinery is the main demanding of hydrogen. Then when we see what is which way that hydrogen is produced, we can see on that slide that more than 90% of hydrogen is produced from natural gas, oil, and coal. And so when we produce hydrogen, we also may produce carbon dioxide. With the table that I show on the right side of the slide, we can see that about 9 kilograms of 9 kilograms of CO2 is produced per kilogram of hydrogen produced. So when we see that in 2023, 100 million of ton of hydrogen was used, and most of that hydrogen was produced from natural gas. That means about 100 million of CO2 was produced when we wanted to use hydrogen. So it's just not possible. We have to find another way to produce hydrogen without producing such high amount of carbon dioxide. So that's why electrolytic hydrogen based on water electrolysis could be a tool, a mean to produce green hydrogen. So there exists four hydrogen production from electrolytic system. So there is either high temperature production or low temperature production. When we talk about low temperature is below 80 degrees C. There is proton electrolyte membrane PEM water electrolysis. anion exchange membrane water electrolysis and liquid alkaline water electrolysis. So it's here on the bottom on the figure, and high temperature electrolysis with a solid oxide and proton ceramic electrolysis cell. This aspect will be discussed by the next speaker, mainly on solid oxide electrolyzer. So I want to highlight mainly on PEM water electrolysis. This is the main target of NICKEFFECT project. So when we talk about proton exchange membrane water electrolysis, there are some advantage and some disadvantage. The main advantage are this technology could provide high current density. So that means high amount of hydrogen could be produced. So usually those systems are quite compact. Then the hydrogen produced is really high purity, and the response time is also really fast. So it could be well suitable to be plugged with a flexible energy profile like a PV or wind energy supply. The main disadvantage are the high cost of the system, low durability, which is by far not as good as liquid anion water electrolysis, and also it requires a high purity water to be used in operation. So how the PEM water electrolysis works? Basically, as I said, you have a membrane able to transport proton from the cathode, from the anode to the cathode. As a catalyst. When the water reaches the anode, it will oxidate in O2 and produce some electrons. And the proton will go through the membrane and will react on the cathode side to produce hydrogen on the cathode. So we have hydrogen production on the cathode and oxygen production on the anode. When we have a closer look, how is structured the cell. So as I said, in the middle you have the membrane electrode for the proton transport. Then you have the anode active layer made with iridium. Then behind you have the carbon fibers. And then you have a titanium mesh to transport the gas when it is produced. And on the anode side, you have a porous transport layer made with titanium and also a mesh of titanium to evacuate the gas and allow the water to reach the active layer. So when we see the picture of this PEM water electrolysis, there are a lot of concern. First, on the materials, platinum, there is a concern about the cost. Iridium, there is a concern about scarcity of this material and also the cost. And for the membrane, which is made with fluorinated compounds, so we have also some issue with the PFAS concern. So all of this make that technology first costly and also with some environmental issue. When we talk about PEM water electrolysis, there are some KPIs that was defined by Europe in order to make it, even more efficient. So here are list the target by 2030 in terms of electricity consumption, 48 kilowatt per kilo, that we can translate in voltage, 1.8 volt, or we can also translate it in efficiency, 82.2 against a high heating value. Then there is also a target about the cost, 500 euro per kilowatt, and also about at which current density this number has to be reached, so at 3 amps per square centimeters, and reducing the amount of critical raw material about 0.25 milligram per watt. So far, we can see in some publication that this target could be already reached. So here on the right side of the slide, we can see two IV curves where we plot the voltage against the current density. And that was shown here is the impact of changing the polymer membrane in between the two electrodes. So there is a Nafion 117 with the thickness of the membrane and Nafion 212 with the thickness of the membrane, which is much thinner. What we can see is at 1.8 volt, we have about 1.6 amps per square centimeters with the thicker membrane, and we can reach up to 3.5 amps per square centimeters with the thinner membrane. So that means with this configuration, we are very close to the target by 2030, and even with a really low critical raw material content. But when we continue on this document, we can see that actually when the hydrogen is produced, and it's even more critical when we increase the pressure, there is an amount of hydrogen produced on the cathode that will go through the membrane and react with the oxygen on the anode. And when the amount of hydrogen is above 4%, we have an explosive atmosphere, and there is some safety issues that could occur. So when the amount of hydrogen in oxygen reach 2%, usually we stop the system. So what we can see is when we have a thicker membrane, so we can go up to the operating condition of the cell can go from 1 amp per square centimeters to above, but we can go lower if not the amount of hydrogen in oxygen will be too high. It's even worse when the pressure reaches 30 bar. When we use a thinner membrane, this phenomena is even more amplified because we can go below, how to say, we can go below here 3 amps per square centimeters. If not, we already reached the limit of 2%. So that means we can't use the membrane, the thinner membrane, because we have large issue, high issue in hydrogen and oxygen. So we have to use the reduce material in order to reach this target here. So another point that I want to highlight on this figure, it's reported the cost breakdown of different materials in a PEM water electrolysis stack. And what we can see is here on the left side of the graph, the critical raw material account for a large impact on the cost of the system. So we also need to reduce drastically the amount of iridium and the amount of platinum in the PEM water electrolysis. So what are the alternatives? So on this figure, we can see what could be used as a catalyst for the anode and cathode on the alkaline solution or in acid. So the first thing is in the acid for the anode, there are not so many alternatives. It's iridium or ruthenium. So the only way to reduce the loading the amount of critical raw material on the anode side is to reduce the iridium. We can't use any other materials as catalyst on the anode. On the other hand, on the cathode side, we can see there is room for large kind of materials could be used to replace platinum. It's also interesting to see what we call the overvoltage. The overvoltage or overpotential is the amount of energy that you have to add more to get the reaction. So lower is this value, better is the catalyst. So of course, on the platinum, for the hydrogen evolution reaction, the platinum is the best catalyst. This value is really low, but we can see that there is some other candidates like a nickel molybdenum, nickel tungsten could be used as potential catalyst for the cathode. So also, the idea to find out the good catalyst is to try to design a catalyst made with different kind of materials that could reach the same properties than platinum. One property which is used is the energy absorption of hydrogen of the metal. So we can calculate the absorption energy of hydrogen on the metal, and if we try to tune some material, for example, nickel and tungsten, we try to find the same energy absorption of hydrogen in order to get the same electrocatalytic properties as the platinum. Also, when we talk about hydrogen evolution reaction, we should keep in mind that it's a several step reaction. Actually, there are three steps: Volmer, Erovsky, and Tafel. And when we measure or we calculate the toughest slope of each step, we can see that the higher toughest slope is for the Volmer, 120 millivolt per decade. That means that step is a rate determining step. So that means it's a more difficult step in the hydrogen evolution reaction. So on that slide, I don't want to go through to all the kind of materials that's been tested in this publication, but it was interesting to show first that actually nickel molybdenum and nickel tungsten are really close to platinum, so it's really good candidate to be used as in replacement of platinum. And also, when we see in the literature what are the materials that have been used as catalyst for hydrogen evolution reaction, we have the toughest slope close to 40 millivolt per decade. That means with those catalysts, the main determining step is the Erovsky because we have 40 millivolt per decade, quite close to the value that was found in the paper here. So yeah, another thing that I wanted to highlight, it's a good thing to have a good catalyst. For in that example, it was a cobalt phosphorus. So we can see the cobalt phosphorus is really close to platinum, but to have a good catalyst is not the end. Actually, then you have to put that catalyst in the electrode, and depending how you implement the catalyst in the electrode, it can have a huge impact on the performance. So having a good catalyst is not enough. You have to also optimize in terms of loading of the catalyst, in terms of the amount of ionomers that you want to put on the electrode, and how that electrode also is produced could have a large impact on the performance of the electrode. So next. So the NICKEFFECT project is structured as is shown here on this graph. So there are different work package dedicated to electrode deposition development. Then to upscale that electrode deposition to a larger scale, and to model the electrode deposition in order to have the most homogeneous electrode as possible. Once the electrode are produced, there are another work package 6, dedicated to the use of this electrode for different applications. Some related to energy application, PEM water electrolysis and PEM fuel cell, and some dedicated to electronics, memory electronics. This is Singulus who is in charge of this activity. So I will mainly highlight my talk on PEM water electrolysis, which is the presentation of today. So in work package 3, they prepare different kind of electrodeposited platinum electrode, and they vary the amount of tungsten on the electrode. And that was found. It's the amount of tungsten could change the porosity of the electrode. So here you have 4 different examples with the increasing value of tungsten in the electrode. And we can see that the porosity, the roughness of the electrode change a lot with the tungsten content. So increasing the tungsten reduce electrode porosity, and so all these electrode will be tested in PEM water electrolysis. So we just at the beginning of this activity, we just received the electrode, and now the test in PEM water electrolysis will be the next step. So to conclude my talk, I want to finish with this main message. So the first, it's PEM water electrolysis. It's a really compact system able to produce green hydrogen, and it's really relevant to be connected to the renewable energy sources because the time response is really small, so really well adapt to fluctuation current profile. There is a new challenge. I mean, a high challenge for finding new materials on the anode, on the cathode, and also on the membrane. So when we focus on the cathode where we have more room to investigate new materials, nickel molybdenum and nickel tungsten seems to be the most promising materials. But the candidate was found, there is also some study investigation on stability, which is also a major KPI that has to be investigated. Then again, a good catalyst doesn't mean a good electrode. So also when this electrode the catalyst is found, it has to be integrated into the electrode, and this is not trivial at all. So now we just receive the electrode based on electrode deposition, and so we are just at the beginning of the story to test those electrodes, and we also have to investigate how this new electrode will behave since the more, let's say, conservative MEA is membrane electrode assembly are usually made with a catalyst coated membrane. That means the catalyst layer is directly deposited on the membrane. So here in the NICKEFFECT, we have on the cathode side, the electrode is deposited on the substrate. So the interface between the membrane and the electrode would not be the same as a CCM. So maybe there is also some investigation to improve the interface between the active layer and the membrane. That concludes my talk, and thanks for your attention. And if you have any question, I will do my best to answer them. Thank you.
Thank you very much, Frederick. A super insightful and interesting presentation on the NICKEFFECT side. Now we will go to Vesna Middelkoop, the NOUVEAU project coordinator from V2. Vesna will present us the development of SOECs, a pathway to a sustainable future. Vesna, feel free to start presenting and sharing your screen.
Okay. Hi, everyone. This is NOUVEAU project, and I'm the coordinator of NOUVEAU project. So there are a number of partners behind us. It will be great to show you what we are working on already for the past 2.5 years. So I will first introduce NOUVEAU project and explain why we are doing what we are doing. That would cover project scope and objectives and our work plan and methodology, and also finally and importantly, what the impact of the project is. So the partners which are involved are kind of quite spread geographically, but also in terms of their multidisciplinarity and expertise. You can see that we have like two research organizations from Spain, from Germany, and another one from France that you heard of, CNRS. We also have a number of SMEs, small companies, which are quite helpful in what we are doing. And we have one medium/industry partner, Cotema, which is working our scale up. So the main focus of all these partners is that we are building solid oxide electrolysis cells. That's a separate technology from PEM cells, what we heard from previous talk, but it was quite a good introduction there to know what type of electrolysers are the main state-of-the-art technologies at the moment. So that leads us to a question, why we actually are focused on hydrogen. The most important is European umbrella above it, that the Net Zero Industry Act is there as a part of, one of the main pillars of Green Deal, which projects the deployment and the need of hydrogen by 2030, and of course extending it to 2050. Hydrogen plays quite pivotal role actually in all the industries. So what the graph on the left-hand side tried to present is that water electrolysis kind of feeds into a number of processes, and if it's done by renewable energies, we consider this hydrogen, green hydrogen, which also benefits entire sectors in industry if used so and brings green products, and by that affects the CO2 emission reductions. So that's why I'm mentioning here the Net Zero Industry Act as something that's very crucial to define our aim. And the aim is to eventual aim is actually to bolster European hydrogen technologies and their application in different industries. So as the previous speaker from the sister project highlighted, we have a number of technologies which at the moment can be mapped out with the differences. And when we do so, when we look at them, the interesting plot, the way to show their not pros and cons, but rather where we stand at the moment, what's the state of the art, is if you look at their efficiencies through their cell voltage and current density, this kind of graph which is shown on the left hand side. Double axes are also showing the capital cost of all these technologies. So the way you look at this, as everybody knows, alkaline technologies are they require the lowest capital cost, while actually having higher cell voltages and in that sense higher efficiencies. However, as our sister project perfectly explained in the previous talk, the PEM cells are nicely fitted in between this graph, which makes them actually quite interesting technology to work on at the moment. And we also have solid oxide cell technologies, whether electrolyser cells or fuel cell technology, but it's based on solid oxide materials. Is that their current densities can get quite high, cell voltages are quite kind of lower, but they still retain higher efficiencies. There, it's worth mentioning here that they're the lowest developed at this stage, at this time of the development, and there by the European Commission a lot of projections towards 2030 and 2050 that they will be following up and picking up on these performances. However, it is worth mentioning the reason NOUVEAU is interested in looking into this, that solid oxide technologies are actually benefiting from type of materials that can be employed compared to polymer electrolyte membranes or fuel cells, because their materials, okay, NICKEFFECT works on it, but conventionally at the state of the art, the materials that the technology is dependent heavily on is platinum group metal based, while solid oxide cells have kind of quite a broad range of materials that can be employed. Quickly, just to take you through the solid oxide electrolyzer cell, how it works. We have, of course, as with any cell, you have both sides. You have one electrode on one side and the other on the other. I'm not going to call them anode and cathode depending in which mode they work, but we also sometimes call them fuel electrode and oxygen electrode. And in this case, fuel electrode is where water breaks into hydrogen and oxygen actually gets transported through the electrolyte. On the other side, the electrons are circulated, which is actually going in line of the powering the cell. Back to the materials, and again, the scope why we work in NOUVEAU on solid oxide electrolyzer cells is that actually we are dealing here with rare earth elements, but since there are quite a lot of choice among them, yes, it can be very laborious to screen so many of them, and digital technologies and machine learning comes into play here. However, we have rare earth elements which are very important also both for European Commission and also NOUVEAU projects where we can work on alternative materials. So we tried to look at the typical maps which are shown where other kind of technologies similar to fuel cells and electrolyzers are compared, like batteries and wind and photovoltaics. And then we see that rare earth elements are quite substantially represented. So they have potential to replace platinum group metals. Also, among these rare earth elements, some of them are light rare earth elements, some of them heavy rare earth elements. There is a choice to be made. Of course, that had to be traded off with the performance. But the main goal, the main scope is to actually look into relative supply risks for these elements. And in that sense, we are trying, alongside, of course, with PGMs and chromium, we're trying to avoid these, which are in a critical supply, and that moves basically the entire project and the technology itself to the green transition scenario from 2030 onwards to 2050. So more concretely, like what is exactly NOUVEAU looking into? So we have, as it's shown in the cell, we have electrode materials, we have electrolyzer materials, and we have also something which is holding the entire cell, which are called the components, which are called interconnects. So if we go one by one, we can see that we are looking in NOUVEAU into composition of this, and of course recovery and reuse. In particular for interconnects, we are looking in replacing or reducing at least chromium. Then the most traditional electrolyte materials in solid oxide cells are based on yttrium. So that we also try to replace and reduce, or at least recover and reuse. So we are playing with all those methods just to basically bring the amount of these critical materials down. And the most important is electrodes and anode as a main part in an electrolyzer, which is traditionally the state-of-the-art, always lanthanum based, and we are looking into totally lanthanum free electrodes. So we're looking into composition and also weigh the materials deposited, and that's done by coating method. We're trying to scale this up and basically save on the use of entire critical rare earth elements. In key numbers, we are kind of aiming to get at least 20% reduced amount of chromium, to get recycling of the materials 50 to 70%, and to at least have 30% reduced amount of lanthanum as the main rare earth element employed in this kind of systems. Another point to look at is, of course, the performance, and that performance is also as a trade-off of the cost of the cell, and number of cells lead to a stack, and then that arises to a cost of the entire stack. So what we are trying to do is particularly to look into metals, those interconnects that I just mentioned on the previous slide, because that cost derives from the cost of metal interconnects. Another key issue, what we are also looking at, and along run times, is actually to check the degradation of the metal interconnects and corrosion that they may suffer from. This is very key, not only to replacing, as we said, chromium, but also looking into the way we are introducing some lower cost metal interconnects with the protective layers. So the number of options are kind of mapped through trade-offs again, and the trade-offs are also presented in some publications. One of this is presented here. Basically, yeah, there is a trade-off between how many megawatts is shown on a year scale, but what we do is actually basically on a very smaller scale in terms of cycling this, and of course the material cost per kilowatt produced. So that's something critical to look at, because that will eventually bring down the cost of the materials. When we look at all these materials, we have a work package which deals actually with predictive models and materials modeling, which is quite substantial. It's based on machine learning, which takes all the existing data that we are dealing with, applies onto it multi-scale modeling, and this multi-scale modeling are introducing different aspects and levels. It's a multi-scale level strategy. So we have at the electronic level or the atomic level, and then further into tailoring materials can be as mesoscopic and then microscopic, basically on a micro scale where we're actually tuning our materials. that all is put into this virtual screening funnel where we get some properties, and our partner QSR Lab is working on it. They developed quite integrated strategies in doing so and came up with a number of materials we are currently testing as alternative materials and compositions for electrodes. More concretely, once we've got this input from modeling and wide range screening of materials, we did kind of proceed to the materials development. We do have companies on board which are doing materials manufacturing, so we are confident that we are able to scale up these materials. That's done by Marion Technologies. The next partner, which is playing quite interesting role here, is actually to produce greener inks. Currently, the inks are based on solvents. What we are trying to introduce here is water-based inks. VXL is the partner which is mixing and developing inks for us. The rest of the partners are trying to deposit inks as an active electrode materials. And we try to look into different ways of depositions. We have a number of techniques. Of course, there is also pre-screening benchmarking as by very conventional methods, as just casting and Dr. blading, but then come into play a spray coating of electrode with sophisticated tools and computer-controlled stages where we can apply larger areas more uniformly. And we also have partner Kotema working on slot die coating. So it's very interesting. We are quite a lot of the majority of project is actually focused on application and deposition of electrode materials. Again, to dive a little bit deeper into this, because every step of it is very crucial. One thing is actually getting the material delivered to you in the right powder form, processing that powder, thermally treating it, milling it, getting it into right suspension form. And that's already quite a big step, even though it sounds as trivial as it is making suspensions. Our suspensions are tested for their stability, also to introduction of different solvents where we are aiming to replace organic solvents by water. The weight percent and the number of additives we are adding into it. Spray coating, it's the next step where we are applying these suspensions and we are having a number of parameters to tune, such as nozzle size, speed size, but that is eventually reflecting into very uniform, homogeneous distributed material. As you can see, some examples there at the bottom of the page. After that is thermal treatment, again, another crucial step because there could be some weaknesses in terms of mechanical strength and cracks, which we try to, of course, eliminate. We are having very careful drying and sintering procedures. And finally, the proof in the pudding is, of course, characterization. First, to start with the distribution of elements and microstructure, and of course, electrochemical testing with using, as it's very conventional, we also seen in a previous talk, that's electrochemical impedance spectroscopy and simply IV curves. Some of the results are just glance here just to say that every time we are depositing electrode layer and assembling a cell, we are doing testing as well and benchmarking that to the state-of-the-art lanthanum-based materials. Another view to the interconnects. For interconnects is, of course, as I said, material selection and chromium amount reduce the paramount of going further into development. Manufacturing itself is essential and done by partner Forschungszentrum Jülich and additional to partners which are looking into the associated partners which are looking into metals themselves. Most important is just to apply the protective coating, which is done by different coating technologies. And then again, proof in the pudding mode is very important. We are spending quite a lot of amount of time on oxidation testing and then post-mortem composition characterization and long-term testing. At the moment, we are having like more than usually 1,000 or 2,000 hours of running these tests. Again, final step is once we are confident that these tests are producing results, we would be assembling these cells into a stack, and that's what makes still solid oxide cell technology slightly different. There are not that varied number of stacks designs. The state of the art, the most conventional stacks are already commercialized by a number of companies which sell stacks. They're on the shelf, but they usually contain very predictable materials, which are rare earth elements, lanthanum-based, yttrium-based, and chromium-based, which I just mentioned earlier in earlier slides that this is something what we actually are aiming to replace due to sustainability requirements. Our partner FEAXEL is working on assembling cells into stack, and they have quite developed system for integration and testing first very short stacks, first cells to start with, and short stacks. So that's where we are finally aiming in this final year of the project, and so hopefully in the next webinar we'll be able to show more results on this integration. What we're also looking into is sustainability and life cycle assessment with integrated recovery and reuse of materials, which is quite important. Attached to these sustainability studies is also toxicity studies and effect of exposure to humans by simply using these materials, and strategy which is for people who work in toxicity studies called safe by design strategy, and that's what we're all trying to integrate and show the complete picture of the alternative materials to the ones which have higher toxicity, and on the other side are very critical, can be replaced in this way. So we have lanthanum materials as a benchmark, but we are looking into lanthanum-free anode materials and their characterization. Then we are replacing yttrium-based electrolytes, and then taking every step of what we just looked at into the account and life cycle assessment to get the entire picture of the impacts. Both ways viewing what we already know about global warming potential and critical raw materials use in specifically this time in electrolyzers, but entirely in a fuel cells and other chemical systems. We have an overview of the life cycle impacts of the number of these most commonly used materials, which you can see on the right-hand side. Scoring high as this having this cumulative energy demand and also global warming potential is actually platinum, as you could expect from platinum group metals. After that come, of course, iridium and some other metals like gadolinium that is also used sometimes in solid oxide cells as protective layer. So that's something that we have to look at, and of course lanthanum is there on the list. So these studies are already done, but within these studies we are trying to benchmark our current materials to that. On the other hand, we also do societal impact and the introduction of hydrogen production technologies, and one of which is solid oxide electrolysis, how they compare, and if there is any awareness of hydrogen technologies on the market that can be compared to that. Also, it is interesting to see how much there is also awareness of the need to replace rare earth elements which are commonly used and shown on this graph, like lanthanum, gadolinium, and yttrium, which we are trying to reduce amount of. And then whether in all of this recycling can play kind of quite a substantial role. As I said earlier, switching to green inks, also trying to eliminate organic solvents and make green ink-based electrodes is one of the very important objectives which we are trying to reach. And that's our team, which is working on the novel electrode coatings and interconnects for sustainable and reusable solid oxide electrolyzer cells. Thanks for your attention.
Thank you, Vesna, for your insightful presentation today. Now it's clear that both the SOEC and PEM Water Electrolysers technologies hold immense potential for advancing a sustainable hydrogen economy, and they each face unique challenges and exciting opportunities. We already have some questions here in the chat. The first one is for Frederick. So, Frederick, there is often a gap between lab scale testing of materials and performance evaluation in single cells. From your experience, what are the know factors that need to be considered to ensure the lab scale results can be meaningfully compared or extrapolated to single cell testing?
It's a long question. Basically, I think in the three electrode configuration, we're assessing the kinetic activity of the catalyst mainly, and usually all the catalyst is immersed in the liquid electrolyte, so the entire electrolyte actually is working. While when we are in full cell test, we have to use some ionomer to extend the reaction more deep in the volume of the electrode, and not have the reaction only at the interface between the active layer and the membrane. So I think this is the main difference between both, and actually it's not straightforward to compare the two approach. One will give you if your catalyst is active, and in the full cell, you also have to pay attention to how you will prepare the electrode to make it all your catalyst active. So it's for me, it's not you are not assessing exactly the same thing.
Okay, thank you for answering the question. And the next one is for Vesna. About the NOUVEAU project, and in your project, what are the main challenges you are facing in scaling up electrode fabrication for SOEC, particularly when using spray coating?
Well, some of these points probably someone picked on along the talk. Yeah, the main challenge is even we got to that we are able, especially with our partner, the company which is able to scale up the powder. So we are not lacking materials, especially once we decided to go for the sustainable ones, so more earth abundant and not critical. So the next one is actually the starting point, as I try to present, is in building up the layers, is having the right suspension. So the suspension has to have quite well distributed material. Of course, the agglomerates, additives, all those things that come into play are very essential. And then once you apply that, of course, you will see whether and that is in answer to this question, that is the most challenging step, is whether not only the entire uniformity across the entire surface area is but just if there are small defects in the coating, some parts which are delaminating or cracking. So just simply mechanical kind of issues which are reflecting basically into the performance of the electrode. So that is typically day-to-day. If you really want to go back to the lab and talk about these issues, yes, day-to-day challenges is that depending on pre-processing and post-processing of the coating itself, the electrode layers are nicely stacking on top of each other, and there is no mechanical issues with them. There is a second one, if we're talking mechanical versus chemical. What is typically known as degradation causes for solid oxide cells is the migration of certain elements from one layer to the other, especially these are solid oxide cells, which means our electrolyte is also just yet another material. So the material should not be kind of diffusing through each other. For that, what we do, we apply protective layers, which kind of curb that migration to quite a high extent. I think, hopefully that answers the question.
We have another one for you, Vesna. Are there specific issues related to achieving uniform coating quality, adhesion, or material compositions at a larger scale?
I think that for that we are quite confident that our coating technologies, both spray coating and slot die coating, will be able to achieve that. The only thing is, as I said, the first start is getting the right suspensions, especially if we are aiming for water-based suspensions. They have still some issues. That's why the widely used solvents, chemically harsher materials are working much better, which we're trying to replace. So yeah, large scale, once we are demonstrating a small scale, these other technologies that we have and what we are now at the moment trying to scale up are working quite well once we produce the right formulation. So I hope that answers the question. So there is potential definitely for scaling up.
Thank you for your answer, Vesna. And there are two other ones just for the NOUVEAU project directly. So are there some KPIs on the mechanical stability of the electrode that will experience thermal stress?
That's a very nice question. That's typically a question, especially I didn't highlight enough that solid oxide cells are working, but I kind of assume that's a pre-knowledge you need to have. I'm working on very high temperatures. Very high is very high compared to other technologies such as alkaline and PEM cells, which are hardly getting to 100 degrees. We are 700 degrees, which we're trying to reduce to 600, but still this is considered quite high temperatures. And at high temperatures, you can expect these mechanical issues, especially when we start looking into degradation modes after 100 up to 1,000 hours, and those 1,000 hours are very crucial in the performance of any cell and even stacks. So with materials which are already state-of-the-art and formulations of the electrode inks and electrode materials themselves by coating, we already know some ways how to make, again, I'm using that word, uniform and homogeneous distributing, not only elementally, but also like entire kind of ink or coating or electrode deposition. However, always the post-mortem analysis can tell us a lot about what happened during operation, because yeah, that's the main issue for the solid oxide cells, and a lot of ourselves definitely, but a lot of other kind of workers, researchers, and even companies are looking into long-term testing after 1,000 and 2,000 hours. So where do we get when and where do we get this degradation of materials? That's the key key question. So some already commercialized, which are lanthanum-based and not that sustainable, are getting into long operation hours, which is kind of already some sort of progress. Now we're trying, especially as NOUVEAU, but there are also other projects for sure working on it, trying to get in the long operation hours with alternative coatings.
And do you think is it possible to produce hydrogen directly compressed as it could be done with membrane-based electrolyzers?
Depends on the scale, how we scale this up. There is also, I mean, yeah, the point is where we're using this hydrogen. Everybody has heard in the projects, we work in projects where the compressor was needed. It's also about how you are integrating this hydrogen into downstream process. What is this hydrogen needed? I'm now talking about specifically solid oxide cells, especially that since we are working, as mentioned in the previous question, on high temperatures, you're having to make right balance of plant and know how to manage this heat which is there and integrate there in a downstream process, which is usually lower temperature process. So that's one thing. And hydrogen as being such material, such fuel which is needed for downstream reactions, usually needs balance of plant, safety considerations. So then we are not working on it. So we are not yet integrating this hydrogen, but knowing from other projects, you need quite a lot of engineering around it, around the stack, and then stack integration with balance of plant into downstream process.
Okay, thank you. And the last question we have is for both speakers. When post-mortem characterization is performed, what are the main degradation mechanisms observed in PEM water electrolyzers and SOECs For PEM water electrolysers, I guess as soon as we remove platinum, we should have some poor durability due to metal leaching. But what happens in SOEC?
Okay, if I can go first, immediately shooting my answer to this. Yeah, that's the right, someone pinned the right problems there. I touched lightly upon that. So one thing is, of course, this mechanical stability in the sense that the coating is nicely adhering to the layers around it, so that there is no little cracks in the coating, so that those are mechanical issues. But of course, as I mentioned, and that's also key, that number of these rare earth elements that I employed, and the electrode materials are perovskite, so there are sometimes up to 4 elements in that electrode. So you do have always one of the more volatile elements which are trying to diffuse and migrate, and we try to prevent that with a protective layer. So there is a lot of iterative work needed here, especially when introducing new materials. But I can surely say that the other more conventional perovskites which have been tested, and which the technology that's been worked on for the last like 20 years has these issues, and there is quite awareness of degradation mechanisms being having the underlying cause of degradation by diffusion of different elements, which brings kind of chemical instability as well as this associated mechanical delamination and cracks within electrode layers. Hope that answers the question.
I think so. And Frederick, do you want to add anything?
Yeah, I mean, on PEM water electrolysis, degradation mechanism are really important, and of course, post-mortem characterization could help to better understand what was the main cause of the degradation. Among them, there is the membrane thinning. So here we consider a non-noble metal cathode catalyst, and if the oxygen reaches the cathode side, it may create hydrogen peroxide. And this hydrogen peroxide could lead to that's called the phantom reaction, so production of radicals that comes to, let's say, erode the membrane and make it thinner. And as I explained in my presentation, if the membrane becomes too much thinner, you could have, let's say, some pinhole and make a short circuit. So this is one damage. Also, the anode side could be the iridium could be much oxidized, and you can lose activity. The bipolar plate made with titanium may be covered with the oxide layer that increase the voltage due to the higher resistance, and so also it could decrease the performance of the cell. And yeah, to have some ideas about which mechanism it's the highest that create more damage, for sure you need some post-mortem like SEM images, XPS measurement that could help you to better understand what were the main mechanisms that lead to the degradation of your cell. So the challenges also about the degradation are also huge. Yeah.
Okay, thank you very much to both of you. This is the end of our Q&A space. It was an excellent webinar. Thank you for the discussions, for the interesting presentations both Vesna and Frederick presented today. And hope we can reach to NOUVEAU again and have another joint webinar between NICKEFFECT and NOUVEAU. We will upload this recording on YouTube. Feel free to disseminate it, to share it among your network, your social media channels. And thank you very much.
Thank you. Bye.
Thank you too.
Thank you.
Bye bye.